Hello, my name is Jaden Finney, and this is my AE2610 lab number 2 titled Digital Sampling. Alright, so this experiment investigates how different sampling rates impact audio recordings, specifically their effect on sound capture accuracy and amplitude representation. Using a DAC, we'll analyze sampling rates influence their reproduction of dynamic audio shifts. By examining the time history of recordings, we aim to clarify the relationship between sampling rate and amplitude precision. This is helpful in engineering with SHM, where accurate data acquisition of time varying signals is crucial. This experimental approach. So in this experiment, I use a LabJack DAC system to record the dynamics of a piece of classical music where the microphone is placed a certain distance from the laptop speakers. The goal is to assess how sampling rates affect the accuracy of the captured sound, focus on changes in amplitude dynamics. So I used the DAC, a USB cable, some screwdrivers, the breakout audio adapter, the microphone, laptop, some jumper wires for connections, tape, the software, and a wave recording of Beethoven Symphony No. 5 in C minor, movement number 1. I chose this one because classical music has more dynamic range compared to modern music to this day. So parameters, so I set the record length to 1,000 samples. I set the microphone distance to 0.10 meters. Laptop and Windows Media Player volume were both 100%. And the audio recording I kept the same. That was a 16-bit 44.1 kilohertz WAV file. And the sampling rates I chosen were 22,050 hertz, which is covers the entire human hearing range. I also did half of that, as well as 8,000 hertz, which is telephone quality, 4,000 hertz, which is used for speech applications, and then 3,200 hertz, which is typically used for basic audio applications. All right, so for the experiment, I connected the DAC to the laptop using the cable. Then I connected the microphones out, ground, and VCC ports to the respective ports of the DAC. Then I taped the microphone 10 centimeters away from the speakers. And then I opened this DAC software. I set the initial parameters. I chose a file and a file name to save on the sampling rate. That was for the time history. And then in Windows Media Player, I clicked play on the audio recording, the classical music song, for about 20 seconds. And I'd save the time history. And I just repeat these steps 4 through 6 to the other 4 sampling rates. These are the data results. All right, so table 1 shows waveform identification and frequencies of the 11 tracks given from each power spectrum. So we found 3 sine waves, triangle, square, ramps, 2 noises, a sum of 3, product of sines, and frequency modulation, as well as their peak principal frequencies. And also we have figure 1, which is from my experiment, which shows the time histories of each of the 5 sampling rates recorded in the audio queue. So as you can see, you can see where the loud part of the songs are present with the larger amplitudes. And as you can see, they're it's the same song, it's just a little off for each one. I'll explain that later. We also have table 2, which shows the approximate computer file size and the changes amplitude of global extrusion of each time history. So we have each of the sampling rates, and then as you can see, as you decrease the sampling rate, the file size does get smaller. And these 2 big things, delta amplitude for max V and min V, are what would be most important here. As I'll explain later, but as you can see, when you typically lower the sampling rate, the delta amplitude for both max V and min V do get higher. So let's talk about that. So the speed of dynamics refers to how quickly changes in amplitude are captured by the DAC. While it may be difficult to see differences in maximum amplitude across various sampling rates, the more accurate representation of signal dynamics comes from observing the change in amplitude between consecutive samples. Delta amplitude shows the loudest and softest points in the next recorded sample, and the more accurate the recording, as it better mimics the original analog sound wave. And as we can see, there's an inverse relationship between sampling rate and delta amplitude. As the sampling rate increases, the delta amplitude decreases, providing more resolution and accuracy. However, this comes at the cost of larger file sizes. And some complications encountered. So during the initial setup, I placed the microphone too far away, which allowed it to be too insensitive to capture soft tones, and so I then moved it up. Also, as you can see, with those in figure 1, where the max amplitudes were differentiated, there was a discrepancy between like how it could start the recordings and where they stopped. So there is some peak misalignment. However, this doesn't really affect the experimental success criteria because that's not really what I'm testing for. And also the 11,025 hertz sampling appears to be as an outlier in table 2. I'm not sure why that quite is. Could be from a higher noise floor due to background noise or a slight shift in the microphone's position during testing. So in this experiment, we examined how different sampling rates impact the accuracy of capturing changes in the dynamics of audio signals. As the sampling rate increases, the recording captures more detail, but also results in larger file sizes. This highlights the trade-off between accuracy and data size, which is important in applications like aerospace engineering, where precise data acquisition of dynamic systems is necessary to monitor dynamic systems effectively. And over here, and these are my lab notebook pages. And thank you for watching my video.